Alright, so in the last video we saw how we use binary search algorithm for finding a word in a dictionary faster than linear search. So in this video we're going to learn the algorithm of applying that same algorithm for searching elements on arrays. But before we jump into that, there are a few terms that need to be discussed. So here in our array, we define what is known as a search region. The region of elements, the set of elements or the sub-array where we look for the key element, all right? So LB here stores the index of the lower bound of the search region. UB stores the index of the upper bound of the search region. I'm sorry, I should have written upper bound. Stores index of the upper bound of the search region. And mid stores the index of the middle element of the search region. Well, I haven't shown mid here, but wait a few minutes. Bear with me. All right. Now, what is the reason for underlining the word index in all three definitions? The reason being I've seen a lot of students that make a mistake, and instead of the index, what they do is they end up storing the element in the lower bound of the search region instead. Note, this does not hold the element. LB, UB, and mid, they all store indexes and not the element. All right. So initially, LB has a value of 0. Always, the first search region that we have is the entire array. From the entire array, we divide that array into two halves. I'll call this the left half and we'll call this the right half. For you, it might be different. Uh, so either we search in the left half or we search in the right half, right? So LB always starts out as 0, right? And UB, as you can see, starts out as the index of the last element of the array, and that is 7. So if the size of the array is n, then we can calculate UB by using the formula n minus 1. Now, for calculating the value of mid, it's done by adding LB and UB and dividing by 2. Note that we perform integer division here, meaning if we get a fractional value, like for instance, if I try to calculate the value of mid using the values of LBs and UBs in this array, 0 plus 7 divided by 2 would give us 3.5. But we are performing integer division here. That's why we are going to consider this result to be 3. All right, just the quotient, not the complete division, right? Not the answer, just the complete quotient. Therefore, mid will be this element. Okay, and moreover, whenever you're applying binary search on an array, please make sure that the array is sorted, either in ascending order or in descending order. In this video, we're going to discuss the binary search algorithm when the array is sorted in ascending order. All right. For descending order, things would just be a little different, right? Okay. Let's move on to the driver. Now, I have hidden the elements of the array present here. Why? Because the array that you're going to get as input from the user, you wouldn't know that from beforehand. All right. So you don't know where to look. Therefore, such that uh, we do not form a bias when you applying the binary search algorithm. I have hidden all the elements. The only elements that we are going to take a look at are the elements at the middle position of a search region. Now, initially, LB and UB starts out to be 0 and n minus 1 for this array. The size of n or the size of the array is 8. So UB would have a value of 7. Now that's 0, not 6. All right. Now, how do we calculate mid? Now, mid, as you have seen earlier, is calculated by adding up the values of LB and UB and then dividing by 2. And we do perform an integer division, and that's 3. Okay. So this is our mid element. So what's our mid element? That's 6. Now, we need to search for the item 13 in our array. Now, let's do these comparisons. Now, what does this comparison mean? Notice that we were I was asking this question very frequently in the last video. Does our word lie in the left half or it lies in the right half? That is exactly the question that we are going to be asking here. So, does our key lie in the left half? If it lies in the left half, that must be lesser than the mid element, right? And what's our mid element? That's 6. Well, this is false. Next, we check if our key lies in the right half, meaning in this region. Well, to check that, we need to test whether our key is greater than the mid element. And it is, right? Therefore, we do not go for checking this. Because that's true, therefore, we need to search in this region. Therefore, LB must be 4. Or, in other words, LB should be reinitialized to mid, the value of mid plus 1. Current value of mid is 3 and mid plus 1 would give us 4. So this is the region where we must search next to find our element, key element, that's 13. Now let's recalculate mid again. So 4 plus 7 by 2, that's 11 by 2, 5.5, and we are going to perform integer division, that's 5. So this is going to be our mid element. Let me rewrite mid such that it's smaller. MID. Alright. So what's our mid element now? That's 10. Let's compare. Is 13 less than 10? Surely not. Next. Let's ask the question whether 13 is greater than 10. That's true. Therefore, our element lies in the right half of the mid, meaning we need to check for this. Following the earlier method, LB would now be mid plus 1 and will become 6. UB would continue to remain 7. Now let's recalculate mid again. Just a second. Alright. So 6 plus 7 by 2, that's 13 by 2, that's 6.5, and performing integer division, we get 6. Now mid and LB have the same value, right? And what it is? That's 13. So we have found our element. So 13 does not lie in the left half. That's false. 13 does not lie in the right half. That's false as well. But the key is found. It lies at the mid position. Therefore, 13 is equal to 13. That's true. Hence, our key element has been found. Now, once our key element is found, we store its position or index in a variable called pos, and we will assign the value of mid to pos because mid is the index where the element was found. And we terminate. Because there's no point searching for 13 any further. We have already found it, right? Now, I guess I have explained what pos holds. Well, pos holds the index where the key exists. Initially, that's -1, indicating the element has not yet been found. But because the element was found, we reset that to mid, that's 6. Now, this was case 1, where the key element exists. The key exists. Now, there may be another situation where the key might not exist in the array, all right? So let's search for the element 0 in this array. Okay, so it starts out as 0, LB starts out as 0, and UB starts out as 7 because the size of the array is n. We calculate mid, 0 plus 7 by 2, and 0 plus 7 by 2, that is going to give us 3.5, and we take only the integer part, that's 3. So this is our mid. Let me make our mid a little smaller. Okay, so this is our middle element. What is this? That's 6. And we're going to compare our element with our key element with the mid element. We see that it's less than 6. That's true, meaning our element is likely to be present in the left half of the mid element, right? Thus, what do you think? Should LB be adjusted or should UB be adjusted? Well, if you chose UB, you would be correct because now UB should be this, meaning UB should have the value of mid minus 1. UB would be 0, LB would be 0, and UB would be mid minus 1, and that's 2. So we're going to search in this region now. Now let's recalculate mid again. So 0 plus 2 divided by 2, that's going to give us 1. So this is our mid element. Now let's see what it is. That's minus 2. Now, is 0 less than minus 2? It's not, right? It's false. Well, is 0 greater than minus 2? Well, it is. That's true, right? Therefore, our key must be in the right half of mid. Now, the right half of mid is 2. Therefore, we must adjust LB to be mid plus 1. And thus, it's going to be 1 plus 1, that's 2. UB will remain 2. And we have to calculate mid all over again. So UB and LB are same right now. All right. So if we calculate the value of mid, 2 plus 2 less than 2, that's 2. Now our mid element is this. So many arrows in one. Okay, now what's our mid element? Let's see, that's 3. Now is 0 less than 3? That's true. Don't need to check any further. Therefore, our key lies in the left half of mid. But wait a second. It lies in the left half of mid. How can it lie in the left half of mid? We have already checked out minus 2, right? Because minus 2 was found in the earlier step as the mid element, we concluded that it must be in the right of it. Moreover, the array is sorted in ascending order. There's no way that our key element would lie in the left of the mid, meaning we need to change UB, right? No, I'm really sorry. Yes, we need to change UB, the value of UB. And the value of UB is always set, if the key lies in the left half, then the value of UB is always set to mid minus 1. And therefore, the value of UB is going to be 1 and LB is going to be 2. If we continue on with this process. But are these right values? For example, can LB be ever greater than UB? Let's go on to the definition that we showed in the first slide. LB stores the index of the lower bound of the search region. So concentrate on the word lower bound. And UB stores the index of the upper bound of the search region. Therefore, it's by definition, LB can never be greater than UB. It should always be less than or equal to UB, isn't it? So this is our terminating condition. And if this happens where LB exceeds UB, that means the element is not found. Element is not found. And thus, we should terminate. And at the very end, if you check the value of pos, it remains minus 1. And that concludes that our key is not present in the array. All right. So this was case 2, where key does not exist in the array. Okay. So let's write a few observations now. We know that LB is initialized to 0 and UB is initialized to n minus 1 for an array of size n sorted in ascending order. Right? Now, for every value of LB and UB, mid is recalculated as follows. Mid equals LB plus UB by 2, and we take the integer part of the division. Now, if an element does not exist, then what would happen? then LB would become greater than UB. Therefore, we must continue searching for an element till LB is less than or equal to UB. Remember this condition very well. Understand it very well. How long should we continue searching? Till the lower bound does not exceed the upper bound. Like lower bound should always be lesser or equal to the upper bound, right? That's what the definition says. Okay. Now, if you still have some doubts, rewatch the explanation of the dry run for both the cases, case 1 and case 2, a few times, and then it will come to you, right? Now, let's move on to the algorithm section of this binary search. So, ARR is the array where we need to search, and N denotes the size of the array, ARR. Key is the element that needs to be found, that needs to be searched for, and LB is initialized to 0, UB is initialized to n minus 1, and the pos is initialized to -1, indicating that an element has not been found. Now, how long do we continue this search? Till LB is less than or equal to UB. All right, let me use a different color. Let me use, not this, let's use this. I can't use that as well. Let me use red. I'm really sorry for using red, but there's no way. I don't have any other color choices left. So, for every value of LB and UB, we calculate mid. Next, we check if the key lies in the left half. Now, how do we check if the key lies in the left half? If the key lies in the left half, then the key must be less than the middle element. Now, if it is less than the middle element, then our search region will be restricted to the left half, and therefore we manipulate or change the value of UB by mid -1. This should be mid -1. Okay. Next, if our key lies in the right half, meaning it lies to the right of the mid element. If it does that, then we need to change the value of LB by mid +1. Otherwise, if the key element is equal to the mid element, meaning the key has been found, and therefore we set the value of pos to be mid and we break out of the loop. Now, that's the algorithm for binary search. All right. It's pretty simple and it's pretty effective as well. We reduce our problem in half and we search and we break down our array into tiny small pieces until we have found our element or until the element is not found. All right. So I hope you understood the algorithm for binary search. And then in the next video, we'll implement the program of binary search. All right. See you in the next one. Bye for now.